Hello guys. Today our topic is deep learning and Pytorch, but the head count is a bit low as of now. So we'll be starting shortly. So hello guys, today we are going to be learning deep learning and Pytorch. So yeah, this is actually a really important topic. So if your friends haven't joined already, please do ask them to join. This forms the basis of the next upcoming session, which is NLP and computer vision. I know a lot of you would be interested in those topics. So for that, this is the basis, and this is the basic foundations which you need. So please do ask them to join. So I'm starting right now. Um, So, yeah, we'll start with basic deep learning. I'll explain what a neural network is to you guys. Then we will see how to implement these neural networks using PyTorch. And then finally, we will have a look at CNNs, which form the basis of computer vision. What is deep learning? So, a lot of you would be from a computer science background, so you would have heard of AI ML, but deep learning is somewhat less heard of concept. So, yeah, as I said, this diagram encapsulates this idea quite well. Um, so deep learning is a subset of ML that's quite big actually. So some people get confused between these topics, but essentially the purpose of deep learning is mostly it's for processing these unlabeled data or for finding exceptionally, intricate patterns. That's where deep learning is useful. So this deep learning concept is based off neural networks, which we are going to discuss in detail now. So there are several use cases of deep learning which you would have certainly heard of. When it comes to NLP, OpenAI, you would have heard of all of this right now. So all of them require deep learning, and this is the diagram of a neural network, which we're going to discuss in detail now. Image, video recognition, speech recognition, all of these complex problems can be solved quite effectively using the concept of deep learning, which is based on the concept of neural networks, which we're going to discuss now. There's so many applications. So yeah, let's start. Uh, what is a neural network? So before we go to computer science or AI, I want you guys to look at this diagram over here, which is a diagram of a nerve cell. So it has its endings, and these nerve cells in the human brain, they're connected to each other, and the function of the brain is based on these connections. And in a similar way, if you look at a neural network, we have these neurons which are joined together um, by they're connected to each other. There's a sequence. For example, I mean, we start at the input layer, we have some hidden layers, and we have an output layer. Typically we feed in our inputs here and we get an output here. It could be anything, like in case of a chatbot, we could have some text input here, we could have some text output here, but that is converted into complex data, is broken down. So that's what we'll discuss later. But yeah, this is the idea behind a neural network, and it's called a neural network because of the similarity it has to a nerve cell. So these are called neurons, and this is a neural network. So yeah, it essentially helps us identify complex patterns in data. So I guess we're done with the basics. Now, I'm going to go into each individual part of a neural network and explain it in detail. We'll start with the neurons. Then we have weights and biases. Then I'll also explain the activation function, the loss function, the optimizer, and the learning rate also. So these are terms which you should have a quite good understanding of. Let's start with neurons. Uh, yeah, neurons essentially it's a circle, is depicted as a circle, and we just store values in it. It just holds values. You can look at it as a container. So each neuron has some, you know, it's generally connected to other neurons or directly to the input source, and it's expected to hold a value. So that's how neurons work. It's the basic fundamental unit of a neural network. So that's what neurons are. The power comes when you connect several neurons together, and they help each other by the means of a special idea which is called weights. So you have some inputs here and you have an output. That's how your neural network works. But how do I know which input is more important than the other? You can't say that, all inputs are equally important. For that reason, to consider that fact, we add weights, which is shown here. So each initial input, it's generally weighted before it is, taken into consideration. So typically, it's as this function suggests, I mean, this diagram suggests, you take the weights, you multiply it with the initial input. This is a dot product because we do all of this in, in terms of linear algebra. So this is a very convenient way of writing it. Then we add in a small control factor called bias. Bias is like, you know, we may have some inputs and some weights, but still our output would not be exactly what we want. For that small extra amount of control, we add like a small control variable, which is called a bias. So it's just small value added after this finding this weighted sum. So essentially, weights and biases, you can consider them to be these floating point values, which you multiply with the inputs to get a good output. So I hope that was quite clear. Now, once you've understood weights and biases, how we take in the input and get an output, some of you may ask, what is the purpose of this activation function? We get this sum over here, and we typically pass it through an activation function. That's how we get our desired output. But the idea behind activation function is that there are two things. So a minor reason is that often at times you would want to bound your value. Let's say sigmoid function, this is the formula. So, you know, as we tend to minus infinity, this value goes to 0. As we go to infinity, it tends to 1. So we know that no matter what input is given to the sigmoid function, its output will always be in the range 0 and 1. So we're bounding, we're creating a limit. So let's say we put a sigmoid and then we store the value in a neuron. You can control the value in that neuron to be between 0 and 1. Same way, for tan h, it's defined to be between -1 and +1. The hyperbolic tangent is defined this way. So we'll know that the output range is this only. So that's an extreme power which we get. But this is not a great motivating factor. The actual reason is non-linearity. So uh, see, I explained in the previous slide that we find the weighted sum for every neuron. We go to the past. I mean, it's associated with neurons before it. So we get the weighted sum and we just add that up. But if you just keep doing this again and again throughout the neural network for every single neuron, in the end you will get something which is of the order some y equal to wx plus b. In the end, it will look like this effectively. If you substitute y equal to wxb within itself and you change the weight, so in the end, the final form will look like y equal to wx plus b. This is essentially the equation of a line, which is y equal to mx plus c. We don't want a line as our result of this extensive, computation. Uh, we don't want linearity. That's what I'm trying to suggest here. Linearity is that you get some input, you just get some linear output. Some lambda times that input is the output. We don't want a straight line. We want complex patterns to be recognized. For that, we need non-linearity. That's what we're doing. That's what is the main objective behind activation functions. ReLU is a very famous function. We have a straight line. This is y equal to x, the for all positive values. For negative values, it's just 0. So this is not linear. A linear function would be y equal to x for all values. So we are breaking up the linearity using these activation functions. So yeah, this is an important thing because if it just becomes linear, we don't have any learning which can occur. There's no complexity. We need that complexity so that it can track important and crucial patterns, in the data. That's not achievable by nonlinear systems. So we need to introduce nonlinearity. So here are some activation functions. You don't have to memorize any of these, but it's better to know some of these. That's why I've specified them. This is a sigmoid function. This is its derivative. So derivative will be needed later on. You'll understand why exactly. But yeah, generally you should know some of these functions and the derivatives in terms of the function. You have sigmoid here. This is the formula, and you have the derivative in terms of sigmoid. So this would be useful later on. Apart from sigmoid, we have tan, which, as I said, some of these functions are bounded, and that's quite useful. It's bounded between -1 and 1. Okay. Yeah, the derivative is also expressed in terms of hyperbolic tangent. So this is another example. ReLU is quite, uh, you know, recently has become more popular because it's quite simple if you look at it. Yes, it's not bounded, but it's not computationally difficult. When it comes to exponential functions, sometimes it becomes difficult and time taking to compute that e power x. So that's not here. So it's quite simple. That's why nowadays it's coming into more relevance. Then we have this derivative. For those of you from an electrical engineering background, this is essentially the ramp function, and this is the unit step function. So you don't need to memorize them. Have an idea. Loss function. So loss function or cost function, it's what we are doing here is that we take some, we start with some weights and we calculate some output. But we from the beginning we can't say that that's the right output. So our objective now should be to find out how much loss or how wrong is our estimation. So initially it will have a large amount of error. But our objective should be to increase the effectiveness of our estimations. We need to reduce this error gradually. For that, we must use loss functions. So it's called objective function or cost function. So in a neural network, we pass some inputs and we receive some outputs. But that may not be the actual output which is expected. When you're training our model, we make some expected output and we have another real output. So we try to find out how different are these, and we just try to reduce this difference as time passes. That's the entire idea of neural networks. So we are just quantifying the error, as I said. So this is one good example. Let's say we have a line and we have some points which are supposed to be best represented using this line. So how do you know that this is the best fit line? You would have seen this in linear regression. So essentially we find the difference between our calculated value and our initial value. That's said to be the best fit. If this is less, then it is the best fit line. Imagine you expand a similar logic to n dimensions. That's the idea of loss function. So you create an imaginary plot which kind of shows you where your difference or your error is minimum. So you get this function and you try to minimize this function. If you minimize this function, your model automatically becomes more accurate. So it's an essentially we converted this complex input output problem into an optimization problem. That's what we have done here. So as I said, optimization problem means you need an optimizer. We have already gone through optimizers in the previous session, but let's go through it once more because some of you may have missed that session. So this plot, I mean, could be any random. This is the depiction of a loss function. So an optimizer is can be visualized this way. These balls. Um, our objective should be to get into the global minima rather than a local minima because global minima will have lowest error, which is like it should have the lowest value, and that's what will give us the greatest accuracy. So for that, these optimizers are like algorithms which can help us achieve this. So these balls they depict the paths. So the balls which reach the fastest, those are really efficient optimizers. Some reach slowly, some reach the wrong location, and all these things can be controlled by choosing a good optimizer. So Adam and all that you have discussed it earlier, so I'm not going into depth, but we'll need this for our neural networks. Learning rate. Okay. So we found out an optimizer just an algorithm which we use to reach the minima. But we find for what we do over there is we find a direction and we move in along that direction. But how long should be each step? That's what is identified. I mean, that's what is defined by learning rate. So, for example, over here, if you notice, uh, you start over here and you gradually move towards, this minima. So, yeah, so the large steps which you take, I mean, I'll just go here. Yes. So let's say you take small steps. You find out where the minimum is, but you at each point you find out what is the most best direction. That's the gradient. I mean, negative of the gradient to be very clear. So you find out the direction, but how big of a step should you take in the direction? If you take small steps, right, you'll obviously reach the minima point, but it'll take too long. In terms of AI language, we call it, it'll take a lot of epochs. But if you take large steps, we have a large learning rate, it's very obvious we could miss the minima. So we'll jump outwards and we'll never get to the minima. This is undesirable. So we need to reach a good intermediate between these two, which will get us to the optimal place with a decent amount of time. It should take a decent amount of time, but yes, it should reach the minimum. So how do neural networks learn? So there are 5 steps. If you understand these 5 steps, you are essentially done with the entire idea of neural networks. So as I told you, you have like this complex chain. Initialization is where you initialize the values of the weights and the bias. For every neuron, it has some associated neurons on one side, and each neuron pair has one weight associated with it. So you have to decide how to initialize these values, and each neuron has one bias associated with it, as I'd shown you earlier. So this initialization must be done first. Then we have a process called forward propagation, wherein you know we just assume that all our assumptions, all our weights we chose, everything is correct, and we do the math. So we get an output now. At the end of forward propagation, you get an output. Loss computation is the part wherein you created some output, you got some output. It need not be correct. Very obviously, when you start off, it need not be the correct output. So yeah, that's what we try to find in loss propagation. That what's the difference between our expected and real, you know, outputs. So we do this calculation and then we try to, do back propagation, which, I'll explain in detail later. But essentially, back propagation gradient descent, we're trying to make a change to each, weights which you had assumed earlier, and we're trying to nudge them in the right direction. Slowly, slowly, we'll change those values so that the error will decrease. So we do this in epochs, which is like training cycles. So slowly we move them closer towards the ideal value through these two processes. So we gradually if we keep doing this again and again, at one point we'll reach a really optimum high efficiency, which is like 98% accuracy, which is desirable. So that's the idea of a neural network, how to train a neural network. So I have this one Slido quiz ready for you guys. So if you could scan it and start answering, it would be nice. But like till now, I hope there are no doubts. Um, uh, just a minute. 1 minute. I'll start sharing again. Something went wrong. Um, yeah, this should be good. Yes. So yeah, these are the options. You could have a look at them and start answering now. Please, even if you didn't understand everything till now, try to use some logic and try to if you want, make a logical estimate or logical guess. So this will just help me understand how many of you are following. And there is no right, and I mean there is an answer, but I want to see how you think of this process. That's the process is more important than the answer. So please give it a try. So I mean, I hope that almost everyone attempts this poll. Okay, I guess I can't wait any longer. So I'm sorry, I have to log the poll. Um, let's look at your answers now. Um, okay, some people said that a lot of people agreed that the weights and biases should be set to zero. It's a good idea, but I will explain why that isn't. Yes, that's the right answer, but this one isn't actually. So yes, I'll explain the problem over here. So I think it will be better if I show it to you in the slides. Yes. So I created a slide for this. That's where I'll explain. Okay, so how should we initialize the weights? Let's say a lot of you felt that you can make it zero or you can make it one, but no, that's not how we must ever do it. So I could see that there's obviously some confusion over there. So, the answers of the poll didn't matter. What you have to understand is that if you make all of these weights, let's say all of them, you make them zero, then, there's no uniqueness between, you see, there's symmetry essentially, if you look at it. So you did let's say you do a forward pass. You do something here, and then in the end, the value of this is zero or something. So it's just symmetric. There's no difference between this relation and this relation. So this symmetry is bad. Our network should be able to find some unique, distinct patterns. If everything is treated the same, then you know we're not learning anything. Actually, if you complete this training in the end, you will get something like this. So all the weights on this side, which is behind this hidden layer, all of them will be the same. All of the weights here also will be the same. So that's not something you really desire from a neural network, because see, this input and this input, they're different. And these values in the hidden layer, they're supposed to be different. If all of them are the same, you're not learning any unique pattern. So for everything, you'll give very ambiguous answers, which you don't want. It's going to be a very horrible idea to do this. So it's a rule of thumb: never make the weights equal. Okay, if you make one weight zero, it's completely fine. If you make like some of them zero, it's fine, not an issue. But making all of them zero, or let's say for the same way, making all the weights one, two, or any value, all weights should never be the same. So in the question I said what should be avoided. So you should always avoid the case wherein the weights are the same. This does not apply for bias, because bias is just a constant. You can put any value, it'll automatically correct itself as time passes. Good. I hope you guys, I'm happy that a lot of you have answered the poll. Let's continue. So yeah, as I said earlier, we can, the values of weights and biases is important. So you must start by initializing these properly. And the best answer, the best practice is just to randomly take. It's very easy. Just randomly take values. Yes, obviously, if you take values randomly, your answer which you get at the first cycle, when you put values in the input and you try to find out what the output is, obviously answer is going to be wrong at the end of the neural network. But our objective is to start with any amount of high error, but we have to reduce this error. And the error reduction capability is what makes neural networks so great. So as I said, let's say this neuron is connected to three neurons. We want to perform forward propagation. What you do, each of these, let's say this is x1, x2, and x3. So you multiply the weights, add the bias, you get this. Now you pass that through, your activation function. This is the sigmoid function, if you guys remember. And this is the value that this neuron will hold. So that is the forward propagation process. You keep doing this, for every single neuron, you keep doing this process again, keep doing this maths manually. I mean, so in the end, every neuron will have a value and you'll finally reach a final answer. So you get an answer, and in the end you will, get an answer, but it's going to be wrong. There's going to be some amount of error in that. Let's say you made a prediction of y hat. This is your answer, which you got by making this. You made some random estimates. You got this, but this was a real answer, which was supposed to happen. Look, now what we're doing is we are training the model. We know the answer. We know the question. We know the inputs. We know the output. So we are trying to train the model by saying that, okay, this is what you said that it was supposed to be the value, but this is the actual value. So if you find the modelers or anything, all of this find error. They calculate error. So the absolute or the squaring that prevents negative positive errors. It just takes the magnitude. You can take mean absolute error, mean square error, root mean square error. All these are just different ways of doing the same thing. The calculating how much error was there. So yeah, you can compare the values, and as we minimize this error slowly, that's how we will achieve an accuracy in the model. So that's what, to achieve that, we need backpropagation. This is the part of the lecture wherein a lot of people lose track, but I tell you, if you understand this, then neural networks is done. So we have made some estimate and we came here, we got some output. Now we have to walk backwards and fix the mistakes which we had made slowly, step by step. That's what's backpropagation. So we can observe and understand all this is just a theory, but what you have to do is you have to go back and slowly we have to, let's say we made some assumption in W1, if you make a change to that. We made some assumption in the bias, make change to that. So if we go backwards along each path, we can find the adequate change required in each weight or bias. Don't worry about this diagram. I'll explain it, with sort of simpler example. Let's say this is our idea. We start with one input. We have, one intermediate layer. This is this one hidden layer, one output. Output is shown as y hat, which, we stop here. And then the cost function is, the error which you're trying to calculate. Now for walking backwards, we change the arrows entirely. So this partial derivatives you see here, if you follow the sequence entirely, like in exact order, you should be able to find the error associated with W1, by just following this sequence. So which is delta J by delta W1. We can calculate the error of cost function associated with this by just multiplying this by the chain rule. So I'll show you exactly how to do that. So in our, we just made some assumptions. I have explained so much concept in here. So we have chosen mean square error as a cost function. You just find out the difference in value, square it, sum it up. So this is the function essentially. So its derivative, partial derivative with respect to this variable is this. Again, we have sigmoid. We just substituted. As I said earlier, the derivative of the sigmoid should be. You can use that shortcut which I told you earlier. Sigma into 1 minus sigma. Use that. You directly get this. So yeah, then this is just a standard value which we use. Well, this is quite obvious. Interestingly, the delta Z2 by delta B2 will be 1. So this is the small difference. Otherwise, the weight bias calculation is almost the same. But for bias, that partial derivative is 1. Let's do some maths now. So you want to find out the error which is caused in the cost function. What is the rate? Uh, for small change in the weight, what is the small change in the cost function? That is what a partial derivative means. Essentially, this is telling you, it's giving an idea of the amount of error which is caused due to this small weight. So you expand it using partial derivatives. Then, as I said earlier, you substitute these and you get an idea of how much error was caused in this cost function due to this. So now if you find out how much this specific weight's contribution was, you can correct it slowly. Same way, I'm just showing this again. So if you find out, you want to find out the error in the cost function due to the, let's say the B1 value. Follow this sequence, do the partial derivatives. As I said earlier, you have these values, use these partial derivatives. Actually, if you want initially, if you're doing this by hand, typically it's not advised. If you're doing it by hand, write the functions on one side, find the partial derivatives, use these values, plug in these values over here. And that's it. You got the error in the cost function which is associated with this B1. Now we found out the error which was caused by B1. Error in the cost function due to B1. We found this. Now we want to fix our mistakes. So that's where we use gradient descent. So we use backpropagation, the optimizer, all that's theory. So we take the old weight. We want a new weight which is better. So for that, we choose this. This is essentially, I didn't tell you already, but this rate of change of, the cost function with respect to W1 is essentially the gradient of this value. So the gradient gives us the direction of greatest increase. So this gives you a direction in which the function increases the most. If you put a minus to that, it gives you the direction of greatest decrease. Along with that, you put on alpha. Alpha is what? This is the learning rate. So essentially, you're giving it a direction that if you move along this direction, by this factor, one small alpha factor, you will minimize this change will minimize our error. So almost all the math you did till now, you use this and you'll minimize the error. You just gradually do this, you update the values, minimize the error. So you keep doing this again and again. This is a good, let's start from first. So forward prop, you learn the values, make some estimate. Okay, let this start again. Yeah. So forward prop, find a value. There's some error. Backward prop, fix those values, fix those errors. Again, move forward. You essentially this stopped in two cycles. You keep doing this again and again until you get some good values of weights and bias. This is the entire concept of neural networks. Now I'll explain batching. It's not essential for the function of neural networks, but it increases efficiency. So typically, if you do this one by one, it's going to be really inefficient. So what we do in general, we receive a bunch of data. Could be a CSV file. CSV is an Excel file. Let's say we can get that much data, but you can't sit and if you pass data one by one, it's going to take time. There are certain problems also associated with that. So let's say we're given 1,000 samples. What if we create batches of 100 and we start training in these batches? And then, the changes which we make it at the end of each 100. We can make 100 groups of 100 and so on. If there's anything left in the end, we just do it as a whole. If this was 1080, 80 is left in the end, we do 80 in one batch. So this is the concept of batching. We break down this big data into small groups and then we perform training. So yeah, if you initially do manual, yeah, this is the chaos. If you see stochastic gradient descent, we would have discussed this earlier, but stochastic processes, they are random processes, so it's chaotic. We have batch processes which are much more controlled. In particular groups, you take it. So there is some better, less chaos. I'll just say it's less chaos. So mini batch is an intermediary which is sometimes used. There are advantages of stochastic processes, advantages of batch processes. With batch processes, you have to know what it is exactly. So it is useful, but it's not exactly always necessary. Sometimes you can do without creating batches. One by one, you can send a data, you can manage. So yeah, it's computationally efficient when it comes to storage, speed, all that, it's fine. And it gives us faster convergence. So that's why we sometimes prefer using batches instead of sending data one by one. If you send data one by one, that's a stochastic process. Any one small big change, it goes off. So we don't want that. That's why we prefer to, use batches. Now I'll go through some code so that you can actually understand what I was saying till now. Okay, 1 minute. So I hope it's visible. So I hope all of you would have heard of an OR gate. An OR gate essentially, yeah, you get input, you find a binary addition. If either of these values is 1, output should be 1. Let us teach a neural network to do this. No, it's not as easy as teaching a baby or learning it on your own. Neural network doesn't know anything about the human world and how we function. So teaching it to a neural network is quite difficult actually. So yeah, that's what I am going to do here. So in this, see how this is the logic which you must use when you're trying to do deep learning. There are two outputs. There's one input. I mean, there's two inputs and there's one output. So two neurons over here, one neuron over here. This is the input layer, output layer. Hidden layer, it can have how much ever you want. See, the amount of neurons comes with experience, but for now I've taken 4. And later on, maybe you will realize that this much wasn't even necessary. Okay, so yes, let's start. So throughout this entire code process, I'm going to try to be as detailed as possible, but certainly you won't be able to understand everything as of such. So for now, I'm going to just go through it. If you don't understand, please refer to these comments I've added. You'll be able to understand. initialization. So we have NumPy. You've seen NumPy. Matplotlib is just to see the plotting. I want to show you a plot. That's essentially it. Now, this is the nasty part. You use sigmoid, you have to write sigmoid. You have to write sigmoid's derivative. And then you have to write mean square error. All of these functions you have to define. You see these, we're just writing the functions in terms of Python language. So yeah, that's the sad part. If you want to do it without any proper framework, it's going to be like this. So for neural network, you need to create a class, obviously. So yeah, we define some standard things. Learning rate, as I told you, the size of each step. We have, an input size, a hidden size, an output size. And here, as I said, you can randomize values. A bias, you don't need to randomize it, so we make everything zero. That's okay. Learning rate is as it is. For a forward pass, yes, here we're just doing the maths. So we have x, and this is essentially the w, and this is b. So we find the hidden input. On one side it receives this, on the other side it must apply the sigmoid to this so that it kind of, it needs activation. So we apply sigmoid. That's a hidden output. Again, we have final input, which again it takes whatever came out over here, it takes that in again, and it finds a dot product, add the bias, again put sigmoid, which is again activation function, give us the output. So to apply neural networks, you have to write everything by hand. So yes, looking at someone else do it and doing it yourself, it will show you how difficult this might be if you're especially trying to achieve huge scale problems. It's going to be difficult. I won't lie to you. So yeah, backward process, you find you essentially this, yeah, you're trying to find out the error, the hidden delta. Yes. So this is essentially you're performing the backward pass and you found the delta values. What, as I told you, the partial derivatives. You're using those and you're updating the values. Yeah, yeah, fine. This is properly how to initialize. What is initialization of? What's the forward pass? What is the backward pass? How to update? You've defined properly. Now let's start training. So in neural networks, first you have some, let's say you have 100 units of data. Use some amount of that data to first train your model and then you test your model. Typically, it's an 80-20 split. That's just a rule of thumb, but there's no some written rule anywhere. You can use any ratio. Over here, we're not doing much. So yeah, we train the data. This, don't mind this. This I'm just storing it so that I can show you a plot in the end. So you do the forward pass, then do a backward pass. You probably got some, yeah, yeah. This calculates the difference and all. So you find out the loss. So after the backward pass, you find out the loss. Then I'm keeping track of the loss. This is just for a plot. Yes. So epoch, as I said, it's like, how you have a time and unit of time. This is kind of, epoch is like how much time should I iterate this process? How much time should I train? That's what an epoch is essentially. So I'm essentially printing it. So I guess 1 minute. This should be okay. Yes, it's printed there. Okay, sorry. Yeah. So yeah, we train the model. For the input of an OR gate, we have these values. 1 minute, this is one typo here. Yes. So these are the inputs, and this is the corresponding outputs. So if it's both zero, it should be zero. Otherwise, it should be one. So this is our inputs. It's four. It's typically it's just four. It's very simple for us, but to teach a neural network is difficult. So then we create a neural network. We define the input, hidden output. We set a learning rate. Then it learns, and then for losses during training, we need to define how many epochs. So for that, we pass the value here. So essentially, yes, we're done. So this one, these losses, how much error was there? So that's what I'm going to plot now, and I hope you guys can understand the trend. So we started off here. There was some huge amount of error. But slowly, as we started nudging ourselves in the right direction, this error plummeted and then it stagnates. That's it, we're done. Once it stagnates, we got a good output. Now, let's say I gave these values as input 0, 0, 0, 1, 1, 0 is 1, 1. It made some estimations. For 0, 0, it's saying 0.011. It doesn't understand integers, so it gave a fraction and decimal output. But you see, these are really close to the actual answers. So we have made progress. So yeah, that's all I wanted to show you. This is difficult, I know, but the reason why it's difficult to solve this problem, we have PyTorch. So I'm going to discuss PyTorch right now. Great. Okay. What is PyTorch? So PyTorch is a machine learning library which was created with the idea of simplifying and training machine learning models. You wrote so much if you saw what I did, and I know a lot of you would have lost track. To simplify this process, we have PyTorch. This it's just a library. It comes with stuff ready made for you to use. It's open source also. It is safe and it's quite trustable because Facebook's AI research lab, which was led by Jan Leku, he was the one who essentially led this, and till now, on Twitter, you'll find him. He's a really influential figure in the AI field as well, alongside Sam Altman. So you can say that this is the scale to which PyTorch has grown recently. So what is the best? I mean, why PyTorch? It's mainly because it's based on Python. It's easy to use and learn. Python is very easy compared to C++. Although recently, I guess PyTorch they have support for C++ too. They have introduced support for C++ too. But apart from that, we have certain other benefits like dynamic computational graphs, and the docs are good. So if you want to learn PyTorch, even after the session you want to follow, you can go to the official PyTorch documentation and follow that. But I will introduce you to the basic concepts. So firstly, we have tensors. You know these. Your maths you would know, but a tensor is like it's beyond the simple 1D, 2D stuff. It's n dimensions. We can't even imagine n dimensions, but we're going to use tensors. So we have npi nd arrays. Instead of numpy nd arrays, we use tensors. Tensors, there's some benefits like they're optimized. So for those of you who can't understand what optimization means, tensors are very fast when it comes to computation. You might have heard of GPUs, so they are built compatible with GPUs and they are very efficient. You can make calculations really fast. So that's the main use of tensors, and you have auto differentiation that was also helpful in backprop. So yeah, nn.module. This is the backbone of PyTorch. It explains what we have to do. So yeah, it serves as the base class for developing on neural network models. It enables easy creation. That's essentially if you want to implement in a neural network or a convolutional. We'll discuss that in the end of the session. If you want to implement this CNN, you need torch.module. Any complex architecture, this is what you need for it. I'll explain in the code exactly what this is. For now, you need to know that if you want to implement a neural network, you need nn.module. So torch.device is essentially you're specifying that, uh, many of you, if you're into the gaming field, you would have heard of GPUs. So if you want a better, gaming experience, faster, like you don't want a lag essentially. So for that, you use GPUs. So over here, we want faster computation. For that, we use GPUs. So torch.device is an important, command which, helps you specify whether you want to run it on your own computer, it's a CPU, or you want to attach it to an external GPU. So this you can control using torch.device. So you can use something like CPU or CUDA for a GPU. So this helps us in computing things faster. Okay, so I taught you about optimizers. So Torch.optim is just implementing optimizers in PyTorch. So it gives you everything ready to use. Just you need to drag and drop it. So you don't have to write any maths. You just need to know this. We need Atom or we need standard. Yeah, you just need to know those names and you can implement them directly. So yeah, like you can pass these parameters and learning rate. That's all you need. You just pass these parameters, it will do the job on its own. So yeah, it optimizes. That's fine. So I guess theoretically I am almost done, but I want to go through, a good example over here. Uh, So now I spoke to you about tensors. So let's see what tensors are. Let's say you want to start working with PyTorch. How do you start? Import torch. I think I explained that. PyTorch is abbreviated as torch. So you had three concepts earlier from basic maths: scalar, vector, matrices. You can directly implement these in PyTorch with no difficulty. Like, if you define torch.tensor of 12, you get a scalar. Row matrix vector. Any like n cross m, I mean a 2D one, you get a matrix. So yeah, using the torch.tensor uh, you know code, you can create any form of tensor. Give this is like for values which you add in manually. Let's say you want to initialize values. For that, you use torch.zeros, torch.ones, and torch.rand. Torch.rand is the most important over here because it gives you random values. So yeah, you give it a shape. Okay, I'll discuss shape quickly. So yes, you obviously know this. This is a 2 cross 3. You know that, but how do I know the shape? So shape is simple if you look at it. So this here, okay. You have two brackets over here, which shows if there are two square brackets, it means it's a two-dimensional tensor. Simple rule of thumb. The amount of brackets, square brackets you see in the front, that's the dimensionality of the tensor. That's all. I mean, don't complicate things. So over here, you see the first bracket. Within that, you have two terms. So the shape is two. Now you go again within each of you found out within the first bracket there are two elements. Within each of these elements, you have three values. So that's three. That gives you 2 comma 3. That's the shape. We call that a shape. So yeah, the shape will be useful later, but you just need to know. Again, for this, within the first bracket, I guess there's one value. Second bracket, you have six values. So yeah, within each you have only one. So this is defined by 1 comma 6 comma 1. This is how you kind of depict the shape of your tensor. We have element wise operations. Uh, there's nothing unique in this. If you have A, you have B, you can add them. Let's say you have 1, 2, 3, 4, and identity matrix 1, 0, 0, 1. If you find the sum, it adds the values. Difference subtracts the value. Multiplication, it multiplies corresponding values. If you see in the definition, multiply corresponding values of two sentences. Please don't think that this is matrix multiplication. They're completely different things. So just if there's 1 year, multiply. 2 year, 0 here, multiply. That's it. So you get A into B. Let's say you want to perform division. You have a matrix here, you have a matrix here, just divide the corresponding values. 2 by 0 goes to infinity, so that's why it's written here. It's very easy matrix maths. This part is where it becomes little, you have to know these things. I suggest you by heart these. You have to by heart. Um, A at the rate B is the best way of, performing matrix multiplication. You have 1, 2, 3, 4, and an identity matrix. We get the matrix back. Dot T is used for finding out a transpose. So yeah, you just get the transpose. You flip it about its diagonal. That's what you call a transpose. So that's what was achieved here. 1, 2, 3, 4 became 1, 3, 2, 4. The same you can apply to other dimensional, like any dimension, but for your understanding, I've made it just 2 cross 2. And if you're worried about what these, I'm just printing the outputs. If you don't use these f strings, also f strings are just for formatting it. So you don't get confused by this. This is just for making it look a bit better to you guys. Otherwise, standard print, you can print A and it will give you the answer. So yeah, don't worry about this formatting. If you want inverse, you should use torch.inverse and give it the tensor as a float. So I mean, you convert each value inside a tensor to a floating point value. So why is this important? Because in the inverse formula, you have the adjoint by the determinant. There's a denominator. So almost certainly, if you're dividing, you need floating point values, right? I mean, automatically it converts it to floating point anyways. But if you by convention and by rule, you have to make it a floating point. Otherwise, you'll get an error. So it finds the determinant of this. I mean, the inverse of this, and you get that as the answer. So that's how you find the inverse. Now we have some more things like some mean, max, min. So I don't know what to say. It's straightforward. Sum will give the sum of all elements. Mean will give the average value 1, 2, 3, 4. Sum it divided by 4. You'll get 2.5. Max, min. This will be useful little bit later on if you want to analyze a tensor. Tensor operations, there are two major operations: slicing and reshaping. So slicing, all of you, I hope you know basic Python, at least in 12th or during our sessions, you would have understood it. Slicing is to cut a particular part of a tensor and get that. But you're not making changes to the original. That's what you do by slice. That's what you call slicing. In Python, vanilla Python, you can only do it for lists and I guess strings. So yeah, that's what we are doing here again. It's the same thing. So just follow my cursor. So firstly, you see hyphen. This hyphen is essentially saying that go inside the tensor, the first bracket, take all values. So within the first bracket, take all values. Okay. But the second dimension, it's saying that within each of these values which you have taken, only take the first term, the zeroth position, which is so within each of these, or here, go inside this and choose only one, or go inside this and choose only four. Collate these values and give it to me as an output. That's how you do slicing. I'll repeat it again. So this is a hyphen which says go in, take all values. Then within each, take the first term and you get the sliced output. Again, reshaping is just to change the shape of a tensor. As I said, 2 comma 3 or 3 comma 2. So if you multiply these, like if it's a 2 comma 3, multiply this, you get 6. 6 is the amount of values inside this tensor. 6 values are there, then you can make it a 1 comma 6 also. It might be a better way of representing the data. So this data, if you make it a 1 comma 6, it kind of changes the shape. So these values are made a row matrix, a row. It's just a vector. Oh, yeah, this would be useful in certain cases. So reshaping, yeah, you should have most of these at your fingertips. It's really important. Otherwise, it'll be difficult. So now I'm going to redo. I had shown you how to do an OR gate using neural networks, but that was probably very difficult. Most of you probably wouldn't be able to follow it exactly. I'll show you how Pytorch can make this really easy. And that's why you should, you know, learn Pytorch essentially. So torch.nn module, I said it's very important. So it helps you in defining layers, activation functions, forward pass. Almost everything you're going to do here is torch.nn module. Autograd is, a feature which is made available in PyTorch. So using that, it automatically finds out the gradient. So yeah, manually, you don't have to type all that sigma into one. You don't have to do all that. It does it for you. That's the beauty of Autograd. So it simplifies the neural network training process. That too, all of these they are time optimized in the sense they're very they don't if you write it manually by code, there's a chance that it takes more time, but this will be faster actually. So it is easy to write, you need to implement uh, you know, deep learning neural networks, and it's also faster when it comes to time wise. So there are some aspects, there are different sorts of layers in PyTorch, like a linear layer, a conv 2D layer. This will be for convolutional layers. So in the next part of the session, we'll go into that as well. We have RNN, LSTMs. We then okay, yeah, that's you don't need to worry too much about that. For now, we're just using linear straight line layers. So yeah, activation functions. I showed you so many. Now it's just one small. It's this tiny. You don't have to memorize anything. If you want to use ReLU, Sigma, Tanish, and using each of these, it comes with experience. So don't worry about what I should use now. For now, I have chosen Sigma in my next problem. Use that. Loss functions, there was mean square error, cross entropy error. So each of these have their own benefits, which you will gradually learn with time, with experience. As of now, I'm choosing mean square error. Optimizers, been taught this earlier. I'm using stochastic gradient descent for my thing. Batching, I've showed it to you earlier. This is how you take the data and break it down into small batches, and then you train in these batches. So again, I'm repeating, if I'm going fast, I mean, I will try to answer most of your doubts, but in case you're not able to, I've added comments in a lot of my code, so you can just refer that directly once it's shared after the session. Okay, let's begin. So import touch, neural network, optim. This you need to import these. There's nothing I can explain over here. Import NumPy, import matplotlib. This is to make a plot. I want to show you the same plot again. That's the objective. So you have an OR data set. This is the input. This is the okay. This is the expected input, expected output. I've made it a plot. So okay, this was not needed. Yes. So 1 minute. Yeah. So I define a class. I just call it whatever you want. I've called it an OR network. So yes. So we define. This is just we're calling that it's just written. Yeah, I don't need to explain that in detail. Yeah, we define a hidden layer, an output layer, and a sigmoid. So we sort of this we're just creating shorthands. Self.hidden is a shorthand for this entire thing. So yeah, that helps over here. And we give it the value beforehand. I think okay, and yeah, we have those values in the end. So you just pass the input and hidden size. It defines a layer. I mean a hidden layer, an output layer, a sigmoid function. Okay. So that was an initialization. Now I'm also defining the forward pass. So it takes the value. Yes, this is where it becomes easy. Just say pass this input x to the hidden layer, apply sigmoid. It's all linear algebra. So, just one small variable is showing an entire range of values. So yeah, you're saying for every value essentially, like find the hidden layer values corresponding to these, apply sigmoid to that. Again, you get this again, go to the output layer, uh, find out what's the output expected and yeah, from the hidden layer, what's the output expected? Again, apply sigmoid, and this is the expected result. So this is how in 3 lines forward propagation is done. Here we just create an instance of the model. So we tell it that start with 2, middle will have 4, end will have 1. This is defining the criteria as we want to use mean square error as a loss function, and for the optimizer we want to use stochastic gradient descent. So I'm just stating these in words. Now let's start training. Uh, yeah, this is just to store this. I want to show you the losses. So this is not really important. We are defining 40,000 epochs. So 40,000 times it does this process. Um, so for epoch and range of epochs, for every single instance, go forward pass. So find out the outputs and calculate the loss. Make the optimizer. I mean the gradient 0. That's what it's saying. I've written it. Do the backward prop and then make changes. These five, that's all you need. This is five is the all. I mean, this is the entire process completed in 5 lines, and then you append it. This is just for my plotting. So yes, that's it. This 5 lines. If you complete this 5 lines, iteratively, you keep doing this again and again. Your loss, as I said earlier, it keeps dropping. And yes, if I plot this, I've plotted it separately. So again, it was better, I feel. So once you get used to Pytorch, you can make use of all these features which are made ready for you and use them, and yes, you're done. You've minimized the loss. Just to show you once, I said, let's pass the same output 0, 0, 0, 1, 1, 0, 1, 1. So these were the outputs. So it's almost the same. Yeah, it's almost the same. This shows that it's giving the output of 98 when the expected was 1. So it has a decent level of accuracy for a neural network. So now we're done with this. I would like to do one last, code implementation, which is, there is a very famous data set called Iris. You will find it on scikit-learn the website. So the objective here is we are given four parameters. Uh, the petal. I mean, I guess it's written here. Yeah, like the sepal width, petal width. So these four parameters are given to us to find out, and we're given a set of flowers, we're given these values, and we're supposed to find out which exact flower species it is. It's a very famous data set, so I'm going to implement it over here. So these were discussed. This one, don't worry about it too much. What you're doing is, uh, basically, once we reach a good value, it'll start walking. Reduce the size of its steps. It will reduce the learning rate. That's all we're doing. So on plateauing, once it's slowly starting to plateau, it'll reduce the learning rate. That's all. And then this is to get iris. All of that is related to iris only. NumPy, matplotlib, obviously. So you need these two. Load in the data set. That's it. You just load iris, you get iris. And in iris, you have data, you have a target. So now we're going to start training. So we have this is essentially the inputs and the output. Actually, we have to scale it and kind of, these are some transformations we need to normalize, the features because we have to improve the performance. So yeah, this, you kind of have to do it because it's difficult to explain exactly what this is. But you need to do this before you get the raw data. Only then you can kind of, make it tensors, PyTorch tensors. Making it PyTorch tensors is like it's like changing the format a bit. So you have to do that. So pass these two over here and you're done. If once you convert the format, you can, this is a very famous line. As I said, you want 20% of the data to be test. So you pass 0.2 here. This is just to control the randomness. It's like a seed. So yeah, that controls the randomness, and we split the input output combination into this. So 80% of data is ready for training. So let's start training. Okay, here we define a model. So yeah, we have chosen only one hidden layer, only one hidden layer in the middle. So okay, so here we define some things beforehand. Again, super. And yeah, first we define the hidden layer. There's certain number of inputs on this side, and there's the hidden size. So we define this hidden layer, and we define the output layer as, there's a certain number. There's some, it receives the values from the hidden layer. So we need to specify the hidden size first, and then the amount of, output size. Output size is saying number of classes because, in our problem statement there are three classes which is expected. That's three flowers, so that's called classes. We just formally call it classes. For this is just, we need relu, so yeah, that's activation. This one, I guess we're just, yeah, we're kind of initializing the weights. Yeah, that's standard. We do a forward pass. So first we send the input to the hidden layer. Again, we pass that through a relu, and then we pass it through an out. So yeah, that's it. Because in the end, we have made an estimate. So yeah, we didn't require relu again. I mean, sometimes you don't need to apply relu two times. It's one is time. I mean, in one layer, it is sufficient. So yeah, now we are setting up values. As I said, I have to rush through this little bit. So okay, you set the inputs and you set the shape. It's all basically you're saying these are parameters. As I said, we have a hidden layer. What's the size of that? This is 32. There are 32 neurons in the middle. Yeah, this is just that. Batch size, learning rate, epochs. I guess I've discussed more of this. Um, as I said earlier, data loader is useful if you want to receive data in bulk and cut it into small parts and then use that for training. For that, you need data loader. So data loader helps you reach convergence, to reduce your value faster. So it's useful. That's why we want to perform batch processing here. And as I said, batch size is 32. So we've taken batches of 32. A total input, we've taken batches of 32. Okay. So yeah, we did that. Then as I said, the device. So I'm just saying use the GPU. Actually, Google Colab, it provides free GPU services, so we can make use of that. Even though you don't have a physical GPU with yourself, you can use the ones which they provide online. So I'm using that. If it's not available, then I do it on CPU. Then we define, this may look very complicated. We're initializing the model and we're just saying that, okay, implement the model on the GPU. Then apply loss. We define, no, actually here we're just defining the loss. We're defining, that we want to use Atom specifically. And then yeah, this is for the plateauing. Don't worry too much about this. But yeah, so In the end, it slowly reduces. Once we reach convergence, it reduces the learning rate. That's it. So we're almost reaching the end. It's a training loop. So this was a difficult problem. Still, we are not. It's not complicated much. Modular training is done. I mean, like one time. You train it once. So we set that to be zero. 1 minute. Yeah, you're just taking the batch from the device from the GPU. Optimize the zero grad is to make it zero. Outputs, find the loss, do backward propagation. Um, okay, this one it's just specific thing. If you want to ignore this, it's just the extremities. We want to avoid that. That's why we're using this. Now we did the backward prop. Optimizer step is saying make those changes. So we're done with training. Now I'm just printing this. Yeah, this I want to show you the loss. I'm printing it. And all of this, don't worry about this. This is just code I wanted to show you. Um, yeah, I just wanted to show you how much the loss is. So initially the error was like 0.25. Now it dropped down to 0.07. If you plot it, again, this is a beautiful hyperbolic graph which tells us that it's working out fine. Now, we had 20% of the data remaining. We tested it on that, and yeah, this calculates everything. Like here, it's comparing. We found out some output. We're comparing that with the predicted, which is the real output. We're comparing both of these, and then we're calculating accuracy. And in the end, we got 100% accuracy, which is which is shown here. Sometimes it ends at 99, 98, but anything above 90 is typically considered to be good. So yeah, I'm done with basic, PyTorch implementation. So yeah, I guess. Yeah, now you guys could give your attendance now. Meanwhile, I am willing to take any doubts which you have till now. So try to clear out the doubts so that just a minute. I guess some of you wanted 1 minute. I'll stop sharing. So yeah, I have shared the collab notebook in the chat, so I guess you guys could follow that. I'll just show the attendance for some time, and then my friend Pranav will take over. And yeah, I guess I hope. Do any of you have doubts? Was it clear? Yeah, because we still have some time. Otherwise, I guess I'll give it over to Pranav. Um, okay, I guess we're running out of time, so I guess Pranav will take over now.
Yeah, I'll share my screen in a minute. Yeah, so I hope my screen is visible and I'm audible. Anshuman, can you confirm whether my screen is visible and I'm audible?
Yeah, I can see your screen. You can start.
Yeah, yeah, great. So, hi guys, I'll be taking up convolutional neural networks for y'all. So, convolutional neural networks or CNNs are basically used for the task of image classification, in which you'll have an image dataset which has numerous images, and it's the job of the program to figure out which image corresponds to what object. So yeah, so obviously since it's involved in image classification, it works on image data. So before we move on to the architecture and the working of a basic CNN, I'll explain to you all how exactly image data is represented in Python. Yeah, so coming to pixels, which form the basic component of any image, a pixel, pel, or picture element is defined as a minute area of illumination on a display screen, one of many from which an image is composed. A pixel can be regarded as the atom of an image. Okay. So on the right, I have attached a high resolution image of an eagle. And since it's high resolution, you cannot see the individual pixels like contributing to the image. All of them blend in very well. So the individual pixels are not visible. But if you zoom in quite a bit into the image, for example, in the region of the eye of the eagle, you can see clearly the boundaries between each pixel, right? So this is just to help you all believe that yes, images, even though the pixels are not visible when we look at the image, it's actually made up of these tiny building blocks. So moving on, each pixel in an image has a numerical value or values associated with it, and the color of the pixel is determined by this value or values in case a pixel has multiple values. So yeah, there's nothing, no need to worry about this values. So basically a pixel has only one numerical value associated with it in case of black and white images. And in case of color images or RGB images, it has three values associated with it. So I'll explain this in the slides to come. Yeah, so moving on, image data in Python is generally represented by arrays or matrices of these pixel values. So as I had mentioned before, each pixel, like in a black and white image, has only one value associated with it, whereas in a color image, it has three values associated with it. So an image as a whole is represented by arrays or matrices of these pixel values in Python. And yeah, image data can be broadly categorized into two main types, which is the first is grayscale images or black and white images, and second being RGB or color images. So the picture on the right is obviously a high resolution image. It's an RGB image or a color image, obviously. Yeah, so moving on to grayscale images. So a grayscale image is basically a black and white image or a gray monochrome. A gray monochrome is basically just an image which is composed of different shades of gray only. Like it's an image which contains different shades of gray but does not include any other color, such as shades of red or green or something like that. So yeah, black and white image has black and white obviously, which are the extreme shades of gray, and it has some intermediate shades of gray as well. And yeah, in such images, the color of a pixel is determined by a single pixel value associated with that pixel, which is an integer in the range 0 to 255, with both the extremes included in the range. 0 and 255 can also be taken as the pixel value. And this is in case of 8-bit grayscale images, which is the most common type of black and white image data that we have. So on the left hand side, you can see a black and white image of the handwritten digit 4 from the very popular uh, image classification dataset known as MNIST dataset. So you can clearly see that you can see the pixels clearly in this image, which indicate it's a very low resolution image. Like on the axis, you can see the number of pixels marked. So roughly it's a 32, I think it's a 32 cross 32 image. So which means each row has 32 pixels. So because it's such a low resolution image, in such an image, you can clearly see the pixels. So yeah, another example of a black and white image, which is of the handwritten digit 5. So yeah, coming to the relationship between the pixel value and the color it takes in black and white images. The pixel value of 0 denotes black color, whereas the pixel value of 255 denotes white. The intermediate integers, which lie between 0 and 255, are basically different shades of gray, ranging from dark gray when the pixel value is near 0 to light gray when the pixel value approaches 255. So yeah, the image on the left is again from the MNIST dataset, and it's the image of handwritten 5. And yeah, you can see the 32 by 32 image, and its pixel value representation is on the right, which is basically a two-dimensional tensor, which basically means it's a tensor with one-dimensional tensors inside. You can see, right? It has two brackets at the start, and yeah, it has numerous one-dimensional tensors inside. So you can clearly see that the first few rows of the image, like from top to up to like somewhere here, all the pixels in these rows are 0. And yeah, that is also satisfied in the pixel representation of the image. All of them are 0. And when we, oh, sorry. Yeah, when we come to the central part of the image where the 5 lies, there are some pixels which are white in color, which means that the pixel value should approach something like 200 or 250, like somewhere around that region. So that is also satisfied. In the central region, you can see many pixels with a non-zero or rather high value of pixel intensity, which shows that these pixels are approaching white color as shown in the image. So yeah, that's how the pixel value and the color of the pixel are related in grayscale images. Yeah, now coming to color images are images which contain multiple color channels per pixel. And what this basically means is you need more than one value to specify the color of a pixel. So in RGB images, we need three values to specify the color of a pixel. And hence they are like, we call them as three color channel images. So yeah, unlike grayscale images that have a single channel, typically representing intensity, varying from black to white. So as the pixel value goes from 0 to 255, it goes from black to white, and you need only one pixel value, hence it has a single channel. Color images represent each pixel with a combination of colors. And yeah, for this reason, you need multiple numerical values to specify the color of a single pixel. Yeah, coming to the key characteristics of color images, the first point being channels. So color images are primarily composed of three color channels, which is red, green, and blue. That's why they're also known as RGB images. And all other colors are produced as a combination of these three colors. So yeah, as I mentioned before, in RGB images, to specify the color of each pixel, you need to give three values. And the first value corresponds to the red channel intensity, the second value corresponds to the green channel intensity, and the third value corresponds to blue channel intensity. And by varying the relative intensities of these three basic colors, red, green, and blue, you can generate a vast variety of other colors. And to back this statement, I have attached an image on the left, which shows how you can produce new colors from these three basic colors by combining them in different ratios. Of course, more colors are like possible to be produced than what is shown on the left. But yeah, this is just a basic representation. The second point is that each pixel in the color image is expressed as a combination of intensities from these three channels, what I've just said. And the intensity value typically ranges from 0 to 255 for each channel, which means so one pixel has three values associated with it. The first one being the red channel intensity, second green channel intensity, and the third is the blue channel intensity. So each of these intensity values lie in the range 0, 255. They assume an integral value in this range, and 0 and 255 can also be the value. So yeah, that's about the key characteristics of color images. Yeah, to reiterate the previous slide, I have shown a color image of a plain red image and its pixel representation. So you can see that in this red image, all the pixels have assumed the color red. And on the right in its pixel representation, the first line printed is the shape of the tensor, which contains the pixel representation of this red colored image. So the outermost dimension, which takes the value of 3, this is basically showing the number of channels in this image. And since it's a color image or an RGB image, it has three color channels, red, green, and blue, which like see, this is the set of red intensity values. This is the set of green intensity values, and this is the set of blue intensity values. So since this image has three color channels, hence the outermost dimension is 3. And this are basically for the dimensions of the image. The 255 in between represents height, and this represents width. So this image is a 255 cross 255 image, which basically means each row in the image contains 255 pixels. Each column also contains 255 pixels, and hence this image has a total of 255 into 255 number of pixels. With this block containing the red intensity values, this block containing green, and this block containing blue. And since all the pixels in this image assume the color of red, like obviously the red intensity values of each pixel have to be far greater than the corresponding green and blue intensity values, which we can clearly see here. All the pixels have a red intensity value of 255 and have a corresponding green and blue intensity value of 1. So yeah, that's the relation between the color image itself and its pixel representation. Yeah, another example is, this is a plain green image on the left, and you can see that in the corresponding pixel representation, for each pixel, the green intensity value again is 255, which is far greater than 1, which is the corresponding red intensity and blue intensity value for each pixel. And another point to note is, in case you want to determine the color of this top left pixel in the image, for a general color image I'm saying, what you need to do is, like these are three big blocks, right? Indicating red, green, and blue. See the top left corner pixel of red, top left corner pixel of green, top left corner pixel of blue. And yeah, these three altogether combined are what produce the color of the pixel on this top left corner of the image. Yeah, the color of each pixel in the image is produced by a combination of red, green, and blue according to their respective intensity values, which lie in the set 0 all the way up to 255. This is we have discussed already. And yeah, I felt it's nice to give another example. This is a color image, like not just a plain red or a plain green image. Is the color of a car or something. Again, it's a very low resolution image. That's why you can see the pixels individually. Yeah, again, you can see the shape is 3, which indicates 3 color channels, red, green, and blue, and 32 cross 32 because low resolution image, it has only 32 pixels in each row and each column. And yeah, now you can see that the red, green, and blue intensity values for each pixel assume somewhat like it doesn't follow a standard pattern because the pixel intensities have to adjust their values according to what color the pixel has to assume. So yeah, this is an example of a general color image and its pixelated representation. Yeah, so now that we have understood the data on which CNNs work, which is image data, we have understood it well. We can move on to the question, why do we need something called CNNs? So yeah, as I mentioned earlier, CNNs are mainly used for the task of image classification. So the question we have here is, what is the need for CNNs or convolutional neural networks? Why not just flatten the input image we have at hand and pass it through a neural network? Neural network is the architecture which Anshuman took previously. So in this question, I think many of you all might not be familiar with the term flatten. So I'll first explain what that is. So look at the image on the right. So let's say we have a 2D grid of numbers as shown here, 3 by 3 matrix of numbers. So to flatten this matrix basically means to take all the elements of a row and stack it one on top of the other like this, and then do the same with all the rows and stack each row one on top of the other. So it's just a way to convert a two-dimensional representation of numbers like a matrix into a 1D vector of numbers. And yeah, so in case of grayscale images, this would be very easy. Like flattening a grayscale image is just the same thing, just the size of the grayscale image might be something different, not 3 by 3. But in case of color images, you all might be confused because there's an extra dimension 3 on the outside, right? It's 3-dimensional. It's not 2-dimensional like grayscale images or like this matrix, which I have shown here. So to answer that, what you do in these color images, which have a third dimension, you just take this red channel first, which is a 32 by 32 grid in this case. First, flatten that out. Then you take the green channel, flatten that out, and take the blue channel, flatten that as well, and you just stack them one on top of the other. So yeah, it's generally just extrapolating the same logic to the third dimension as well in case of color images. So yeah, so conversion of the image to a 1D vector is necessary because inputs to artificial neural networks are generally 1D vectors. So yeah, now that we understood flattening, we'll move on to the answer to this question. So with today's level of technology, an image of resolution 256 by 256 is also considered as low resolution. So such a low resolution image itself, when flattened, will the 1D vector which results from the flattening of this image will contain 65,536 elements in case of grayscale images and will contain 1,96,608 elements in case of color images. Like there's a factor of 3 also being multiplied because each pixel needs 3 values in case of color images. So it's not suitable to have such a high dimensional vector as input to our artificial neural network. So yeah, we can ask another question following the previous question that why is it not suitable to have such a high dimensional vector or a vector with so many elements as input to our neural network? So yeah, that is the question on top. So yeah, the answer to this would be the first point is high dimensional inputs increase the number of neurons in the input layer. So you must be knowing from what Anshuman explained to you all that the number of input neurons in an artificial neural network is essentially equal to the number of elements in your 1D vector, which is going as input to a neural network. So higher the dimension, the more the number of neurons in the input layer. And this will lead to an increase in the number of parameters in the neural network because the parameters or the weights to be specific associated with the first layer of the neural network, they increase with increase in the number of input neurons. So yeah, increase in the dimensionality of the input will definitely increase the number of weights in your first layer, which increases the number of trainable parameters of your neural network. The third point is an increase in the number of parameters of the neural network can lead to overfitting because your model becomes more customizable. It can tend to learn the noises in the data, which will lead to it performing poorly on your validation and your testing data set. And obviously, this will also make the training of neural network computationally inefficient because you have a much larger number of parameters to train, right? So yeah, these are the reasons why you cannot just simply take an image and make it a 1D vector and pass it through a neural network. Yeah, so now that we know why CNNs are useful, I mean, the need for a CNN, we'll move on to its architecture and its working. So convolutional neural network is a model architecture developed for the tasks related to image data, such as image classification. This we already know. Yeah, the basic units of a CNN are the following. First are the convolutional layers. Second are the activation functions. Third are pooling layers. And the fourth are fully connected layers. And this fourth point, which says fully connected layers, this basically refers to a neural network, the architecture which Anshuman took up. That same thing is present at the end of a convolutional neural network, as shown in the image on the right hand side. So this part of the architecture you must obviously not be knowing it at this point, but we'll see everything step by step, and by the end of the session, you'll know what this section is as well. You'll already know what this is. So moving on. Yeah, so before I explain convolutional layers, I'll first explain to you all what the convolution operation is. So the convolution operation mainly involves the sliding of another smaller matrix over a channel of our input image. At each point, a dot product operation is performed between the smaller sliding matrix and the area of the input channel, which this sliding matrix covers. So to help you all understand this, I've provided a visual uh, representation of whatever I just said. So in this case, the smaller sliding matrix which slides over our input image channel is clearly of dimension 3 by 3. We must have figured that out. So just imagine like this is our input image channel, the blue thing, and on top of it, we have a 3 by 3 matrix moving around. And at each step, like when that matrix stops, a dot product operation is occurring between this smaller matrix and the pixels of the input image channel, which this matrix covers. So dot product basically refers to a multiplication of the corresponding elements of the smaller matrix and the region it covers on the input image channel and summing all these products up. So this is what a dot product operation is. And whatever we obtain out of the dot product, which is a scalar, which in other words is just a number, this becomes an entry for the output what we get from this convolution operation, which is also a 2D representation of numbers, as shown by this white grid which is being formed. So we shall now see some of the related terminology to convolutional layers. Yeah, the first one is kernel. So a kernel is the smaller matrix which is sliding over the larger image channel. This shadow kind of thing which slides over is this 3 by 3 matrix of numbers is what the kernel is. The dot product operation is performed between this smaller matrix or kernel and the pixels of the image channel, which it covers. And the second thing is activation map. So the two-dimensional representation of the image, which is obtained after the kernel is done sliding or convolving across the height and width of the image, is what is called the activation map. So in this case, the white grid of dimension 3 by 3, which is being formed, is the activation map. So on the right is a nice explanation about how the dot product is done and how the activation map is obtained from the image and the kernel. So first the kernel will be over A, B, E, and F. And yeah, it will do the dot product operation, which will give AW plus BX plus EY plus FZ, as shown here. Then after that, it will come over B, C, F, and G, and again do the same thing and give this, and so on everywhere. And you can see that the input image is of dimension 4 by 4, whereas the output is of dimension 3 by 3. This is simply because this kernel is of dimension 2 by 2. So first it will be here, dot product will occur. It will move, it will go to B, C, F, and G, dot product will occur, and it will move again. Then it will do dot product with this C, D, G, and H. But after that, it has nowhere to go, right? So then it will go down here to E, F, I, and J. That's why each row in the activation map has only 3 entries. And the same reason why each column has only 3 entries. So yeah, so you can clearly make out from this that the kernel size has a say in the size of the activation map, size or dimension. Yeah, coming to stride, this parameter determines the number of pixels by which the kernel moves or slides. It determines how much the filter or the kernel shifts or moves after each dot product operation. So in a way, stride is just the step size of the kernel. So you can see in case of stride equal to 1, like first the like assume the kernel which slides over our input image channel is of size 3 by 3. So yeah, first it will be in the region bounded by blue, then it will just take one step, so it will go to red. It will take just one more step, so it will go to green and so on. But when stride is 2, it will be in the blue region and then it will take a jump of 2. So it will then go to red and then go to green. So I think it's really easy to understand with this example what stride is. And again, I want to bring this to your attention that the input image channel in both cases is of the same size, which is 7 cross 7. But in the case where stride is 1, the size of the activation map becomes 5 cross 5. This is because, see, you just slide the kernel and see, like you can first it will be at blue, then at red, then at green, then it can still cover like most steps, right? So you'll get more dot products, you'll get more entries for your activation map, and hence it's 5 cross 5. Whereas in case of stride equal to 2, it's at blue, it takes a step size of 2, it's at red, takes a step size of 2, it goes to green, and then yeah, it can't go anywhere else, right? So that's why each row has only 3 entries. So yeah, you can clearly make out that stride also has a say in the size of the activation map. Yeah, now coming to padding. So padding just refers to like you have an image, okay, a 6 by 6 image in this example. It just refers to adding like some pixels with some values to the border of your image. Like how it's mentioned here, the most common type of padding is zero padding, in which layers of pixels containing only zero values are added to the border of the image. So yeah, I think this definition is really easy to understand seeing this visual example. And yeah, the reason behind doing this is to control the size of the activation map produced. Because if you like have an image and you do padding over it, you're essentially like modifying the dimension of the input image. So you're modifying the indirectly modifying the dimension of the output activation map. So yeah, this is the reason behind padding. Yeah, so I have a question for y'all. Just scan the QR here to access the question and Vote whichever answer you think is correct based on what we've learned till now. I'll wait for about a minute. In the meanwhile, if anyone has any doubts, you can ask away. I'll wait for another 30 seconds. Oh, wait, actually, since the question involves some calculation, I'll actually wait for a minute itself. Okay, guys, so the time is up. So I've logged the voting and let's see the results. Yeah, so that's really good. The answer is 8 cross 8, which many of you all got correct. Yeah, that's nice. Anyway, if you got this question wrong or you made some mistake, it's fine. There's no need to be sad or anything. Anyway, yeah. So I'll move on. Yeah, so there's a simple formula which relates the dimensions of the output activation map as a function of the input channel dimension, the stride, padding, and kernel size. So this is the question which I'd given you all actually right now. I'd given you all the input channel dimension and I'd asked you all to figure out the output channel dimension given the padding, kernel size, and stride. So there's a direct formula itself. It's very intuitive. Like you can derive this by yourself. So N out is equal to N in plus 2P minus K divided by S plus 1, where N out is the activation maps dimension. Actually, N out cross N out will be the activation maps dimension. N in cross N in will be the input channel dimension, and P is the padding, S is stride, and K is actually the kernel size. Like whatever, if it's 3 cross 3, 5 cross 5, etc., K will be 3 and 5 respectively. So yeah. Yeah, so when we initialize a convolution layer in Python, apart from kernel size, padding, stride, and etc., like we have to pass in two more arguments, which are in channels and out channels. So I have attached below an image of an initialization of a convolution layer. So this is how it's initialized. So you can see two additional parameters which you haven't explored yet, which is in channels and out channels. And yeah, the remaining are what you already learned about. Yeah, so coming to in channels. So a common misconception which even I had when I was learning about how to code convolutional neural networks was that only a single image channel can be passed to a convolutional layer. I thought that for a convolutional layer, only one image channel or one 2D representation of 2D grid filled with numbers can be passed as input, and there's one kernel which convolves over it, and we get one output activation map. That's what even I thought. But the reality is that many image channels can be passed at once to the convolutional layer. For example, we can also pass in color images to convolutional layers. So when we pass in a color image, the in channels parameter assumes a value of 3 because you're passing in three 2D grids of numbers. The first grid is filled with red intensity values, second is green and then blue. So in channels will become 3 in that case. Yeah, another misconception is that each convolutional layer has only a single kernel. Actually, there are as many kernels as the number of input channels for every output channel. So this sentence is fairly complicated and you all might have not understood it right now, but yeah, it'll get clearer as we go. Yeah, out channels. The number of activation maps or channels that are to be outputted by a convolutional layer is what this parameter is. So this helps in determining the total number of kernels, obviously, because I had mentioned that the number of kernels for every output channel is equal to the number of input channels. So this statement, when formulated mathematically, it boils down to total number of kernels equal to number of input channels multiplied by number of output channels. And yeah, it helps in determining the total number of kernels as well as the number of bias terms contained in the convolutional layer. So actually, I have not spoken about this bias term yet. So basically, for now, just know this much that the number of bias terms associated with a convolutional layer is equal to the number of output channels. So yeah, a pictorial representation of how the computation occurs. So let's say you have a convolutional layer with the input containing three channels, which are represented by three matrices here. They're shown by three matrices, and it has two output channels, which is again shown by two matrices. So now this will have a total of 3 into 2, as I mentioned before, 3 into 2 number of kernels, which is a total of 6. So these are the 6 kernels, and these 6 kernels, you can divide them into two groups of 3 each. Like this first group of 3 kernels will help in the formation of this activation map, and this group of 3 kernels will help in the formation of this activation map. And what basically goes on is this first kernel will convolve across the height and width of the first input image channel. The second kernel will convolve like across the height and width of the second input channel. And the third one convolves with the third channel. So when you do this, when you perform these three convolution operations, you will be left with three intermediate activation maps, right? So from those three intermediate activation maps to come and arrive at this final activation map, what you do is you just sum all of them up, because you can do that because the dimension of each intermediate activation map will be the same. So you just sum up the corresponding elements of the three intermediate activation maps to arrive at this final activation map. And you do the same thing, but with these three input image channels and the second set of three kernels. And again, form the three intermediate activation maps, sum them all up to arrive at the second final output channel. So this is how convolutional layer calculates the multiple output activation maps when multiple input channels are provided. So yeah, this is again like an example where the calculation has also been done. So yeah, here we are showing how each output channel is calculated, output activation map. So you can see that I had mentioned before that the number of kernels is equal to the number of input image channels for every output channel. So for this one output channel, you'll have two kernels because the number of input image channels are two. And you perform convolution with this matrix over this and with this 2 by 2 kernel over the second input channel. So you'll get two intermediate activation maps. You do this convolution, you'll get one. You do this, you'll get another. You sum both of them up and you'll arrive at this final activation map. So yeah, so you can verify whatever I told you in the earlier slide about how we arrive at the values of the output activation map. Like basically, if you want to just check the calculation of this top left element, which is 56, when this convolves over this input image channel, the first element will be 1 square plus 2 square plus 4 into 3 plus 5 into 4, which is I think it's 37. And yeah, for the top left element in the convolution between these two, this image channel and this kernel, it's gonna be 0 plus 1 square plus 3 into 2 plus 4 into 3, which is 19. And if you sum both of them up, 37 plus 19 is 56, which is the top left entry of our output activation map. So that's how the calculation goes. Yeah, the example on the previous slide reiterated a statement that the number of kernels in a convolution layer for each output channel is equal to the number of input channels. We've taken two because there are two input channels. And yeah, hence this formula, the total number of kernels is the product of input channels and output channels. Yeah, so now y'all might have a doubt in mind that what is the point of having so many kernels, right? So I'll just give you an intuitive understanding of this. So in actually in when you handle image data, there are different kernels for different feature extraction techniques. Like there are specific kernels, like there's a specific 3 by 3 grid filled with some specific values for probably edge detection in the image. And there's another 3 by 3 kernel, like many of them, which perform smoothing or blurring of the image. So these kind of things might be required for some image processing tasks. So yeah, this is just an example, but when you have multiple kernels in a CNN, they perform some feature extraction task related to the what you what the model needs to do, the task it has at hand. So yeah, with training, it'll learn its weights and it'll customize it in such a way that it performs the feature extraction required to arrive at what class the image belongs to. So that's the point of many kernels. Like each kernel has some minute feature extraction task, which helps in determining the class of an image. Yeah, so coming back to the bias parameter associated with each output channel in a convolutional layer. So number of bias parameters, as I said earlier, is equal to the number of output channels. And yeah, the bias parameter associated with an output channel is basically added to each element of that output channel. So yeah, basically what this means is, let's say I have two output channels, okay, two output activation maps in my convolutional layer, and one of them is this. So each of the two output activation maps will have one value of bias associated with each of them. So let's say the bias value associated with this output activation map is 2. That basically means that the value 2 will be added to each pixel after all the convolution is done. So the bias parameter is 2. That means after the bias added to each element, this will become 58, 74, 106, 122, and so on. So that's how the bias term works. Yeah, the point of bias is just to again add like help your model learn more features about the data, and it also helps to produce non-zero outputs in cases where the region of the kernel which is covered by the kernel in the input image channel consists of only 0 pixels, because then each product term will be 0 and the total dot product will be 0. But in case you need a non-zero value to be present there, the bias term will help with that. So yeah. Yeah, now coming to activation functions. So there's nothing different here. It's more or less what Anshuman explained in ANNs. They, the same set of activation functions are also popularly used here as well, and they help to learn nonlinear characteristics and complex relations present in the data. Yeah, now coming to pooling layers. So we had earlier discussed why, like how we cannot just flatten an image and pass it through a neural network, right? We have to reduce its dimensions. So that's the whole point of pooling layers. So pooling layers in a CNN perform dimensionality reduction while preserving as much information as possible. Yeah, so there are different types of pooling, such as max pooling and average pooling. We'll talk about max pooling because that's the more popular of the two. But if you understand this, you yourself will be able to figure out what average pooling does. So pooling is basically there to reduce the dimensionality of the data before we pass it into the ANN, which is the last stage of a CNN. So max pooling involves a kernel of a certain dimension which slides over the image channel. So since this also involves a kernel of certain size which slides over the image channel, we need to specify the parameters, kernel size and stride, the size of the matrix which slides across the image channel and the step size. So I have like explained max pooling with an example on the right. So how max pooling happens is the kernel of the specified size, it slides across the input image channel. And at any point when it's sliding over the input image channel, whatever pixels are covered by that kernel, the maximum out of all those values is picked up and it's added to the final output. Like all the remaining pixels are ignored. So an example of this, like in this example, I've done max pooling has been done with a kernel size of 2 cross 2 and a stride of 2. So first the kernel will be present here. After that, since its stride is 2, it will move on to the yellow block. then it'll move on to the purple block since stride is 2 and again to the green. So yeah, when it covers the region of the red block, the maximum is 20. So only 20 is picked and added to the final output. When it's on the yellow block, 30 is the maximum, so that's added, and so on for the purple and green block as well. So you can clearly see that max pooling has reduced the dimensionality of data, and you can also see that when you do max pooling with a kernel of size 2 and stride 2 is the most common form as far as like I think most of the places I've seen this being the common parameter specification. So you can clearly see that in this kernel size and stride, out of every 4 pixels, only one is picked out, which is the maximum of those 4. So this basically converts a 2n cross 2n image channel into n cross n because you're dividing the total number of pixels by 4, and this division by 4 is split equally into a division of 2 over the what do I say, the rows and the columns. So a 2n cross 2n image becomes an n cross n image. Yeah, so at the end of a convolutional neural network, after all the convolutional and max pooling layers are done, fully connected layers or an artificial neural network is present. So the content of all the channels that we have present, like before the ANN stage, yeah, all of it is flattened to form a 1D vector, which is then passed into the neural network. And in case of classification tasks, the final layer of ANN will have as many nodes as the number of classes, and it will have a softmax activation to output probabilities. Like if you have 10 classes, then you'll have 10 output nodes with the activation of softmax so that it converts whatever numbers are there at the end of each node into probabilities. So yeah, that's what happens at the end of a CNN. So here I've provided a pictorial representation of all the components of a CNN together. So now you'll be able to understand this. So the input is a one-channeled grayscale image of the handwritten digit 2. So it's first passed through convolution, then a max pooling occurs, then again convolution, again max pooling. And you can see that one channel has given rise to n1 number of channels, which means in that convolution layer, which is con1, in channels was 1 and out channels is n1. Similarly, here you can see in channels is N1 and out channels is N2 and so on. And finally, whatever activation maps we have at the end of the second convolution and max pooling, we just flatten all of it and pass it through a neural network at the end. And all this has been done so that we can reduce the dimensionality of, see, at the end of the day, we're doing the same thing. We're just flattening everything, whatever we have. But what we have achieved is we have, through convolution and max pooling, we have tried to compress all the information of our image into a lower dimensional 1D vector than if we just took the raw image and we just flattened it out. So that's why the like CNNs are pretty good at image classification tasks. Yeah, moving on to code implementation. Yeah, actually, this is the second attendance QRs. It's the same QR, but I'm showing it now. So mark your attendance if you haven't already. I'll wait for 30 seconds.
Pranav, there are some doubts in the chat, so maybe if you could see them,
Okay, wait.
if
Actually,
possible.
I'll just see it in the end. Like only code implementation is left, which is pretty simple. Like
Okay, okay,
we're
okay.
little short of time.
Yeah, no issues. I'll reply to them in the chat.
Yeah, yeah, sure. Yes, I hope y'all are done with marking your attendance in case you hadn't already. So yeah, now we'll be moving on to the code implementation where I'll just show you how Pytorch simplifies the task of passing our image to a convolutional layer and what exactly happens in the background when we pass an image through a convolutional layer. Just a second. Yeah, so this is the code. I
Pranav,
hope you're
sorry
able
to
to.
interrupt you again, but I guess they don't
Yeah,
have view access for this file. Uh, no, I'll
for
share
which
the
file?
link. No, others like just give them view access
Wait, they
under
can't
share.
see me sharing screen.
No, no, the screen is visible, but like I'm sharing this link, the link of this document to them. So yeah,
My
under
collab?
share,
Oh,
yeah, yeah, give them view access.
I'll give them view access. Yeah. Yeah, so I think now they'll be able to see it. Yeah, so yeah, moving on. First comes the import. So I've imported matplotlib.py for plotting functionality. And yeah, torch and torch.nn. Torch I've imported for incorporating tensors and their associated functionality. And torch.nn is to provide all the functionality required to develop neural networks and convolutional neural networks. So it basically makes the function of each small section of a CNN just one line of code, which would otherwise be pretty tedious. Here I'm just setting the seed so that because I'm randomly generating a tensor, so for reproducibility or like every time I run this code, it should produce the same tensor, what I had probably when I ran the code yesterday. So that's why I'm setting the seed. And yeah, so first I'm generating a random tensor, which each entry will be a random integer from 0 to 255. And the shape of this tensor is 3, comma 256, comma 256. So this is basically the sample image. Just treat this as an image, which like I'll pass this tensor through the convolutional layer to show you how the convolutional layer treats an image. So just treat this as a sample image. It's just a randomly generated tensor. And yeah, 3 is for 3 channels, red, green, and blue, and 256, comma 256 specifies the dimensions. So this is each row will have 256 pixels and each column as well. And converting the image to float data type because some coding related errors occur if the like this generates the like each entry will be of type int. So just converting it to float, nothing major. Yeah, so I print the image size, which is 3, 256, 256. And yeah, this is what the sample image looks like. So yeah, this is the red channel, this is the green channel, this is the blue channel. It's randomly generated, but I want you to think of this as some image, like representing something meaningful. And yeah, just to make you believe further that this is indeed an image, I've plotted it as well. And since we've randomly generated, it's something meaningless, but nevertheless, it's an image. So yeah. Yeah, to show you how a convolutional layer works, I'll first start off by initializing it. So conv layer equal to nn.conv2d and yeah, specifying all the parameters. So in channels is going to be 3 because the tensor we've generated is of shape this. And yeah, out channels is 2 so that yeah, I've kept it pretty small so that because I want to show you all the calculation from scratch as well. And yeah, kernel size is 3, stride is 1, padding is 0. So all this should be easy to understand. So yeah, before passing it through the convolution layer, this is the image, its shape and its pixel representation. And now I pass the image through the convolutional layer and assign it to output. So the shape of the output is now, you can see it's 2, comma 254, comma 254. So the 2 is basically because we had our out channels as 2 and 254, comma 254, I think you yourself would have understood that it's because our kernel is of size 3 cross 3. So if you remember, I've shown you a formula n out equal to nn plus 2p minus k divided by s plus 1. So if you substitute the values of n, k, p, and s in that, or you can intuitively also like come to this conclusion that the output map will be of each output activation map will be of dimension 254 cross 254. And you can see that since it's been like just initialized, right? So all the kernels in the layer will be randomly initialized. And yeah, the convolution operation, etc., will occur. And you can see that each of the entries in the output activation maps are different as compared to the input image channel. So yeah, this is the output from the convolutional layer, it has two activation maps because our out channels was two. So yeah. Coming to parameters of the convolutional layer. So I'll first start off by showing you all the kernels. So because the in channels parameter was 3 and out channels is equal to 2, the total number of kernels will be 2 into 3, which is 6. And yeah, uh, you can print the kernels by like this statement, conv dot weight. The kernels are referred to as weights. So first I printed its shape, which is a four-dimensional tensor, 2, comma 3, comma 3, comma 3. So I'll break it down for you all. So basically, in channels is 3, out channels is 2, total kernels is 6. So you just split these total 6 kernels into two groups of 3 each. So the split into two groups is what is shown as the outermost dimension. 2, the total number of groups of kernels. And each of the two groups of kernels will contain 3 kernels each because you have 3 input image channels. So that's why this 3 is there. So two groups containing 3 kernels each. And this 3 comma 3 is because the size of each kernel is 3 cross 3. So when you print this, you'll understand better. You have two groups, first group, second group. Each has 3 kernels of size 3 comma 3 by 3. So yeah, these are all the kernels in our 2D conv layer. And yeah, coming to biases. So because we have only two output channels, there'll be only two biases in this convolutional layer. And yeah, if I print them, you can see the first bias is this and the second bias is this. Yeah, so now we'll verify, like I had shown you all earlier, right? How like in this slide, just a second. Yeah, in this slide, this and this, how the output channels are calculated. So to verify whatever I just said at that time, I'll perform the calculation from scratch. So this is the output. These are the two activation maps which we obtain as outputs from our convolutional layer. This is the first map. This is the second map. So we'll just try to calculate the value of the first entry of the first map, which is 79.2705. So I'll store this value in a variable called first underscore element. So if I print it, you can clearly see 79.2705. Yeah, so now, since we're trying to calculate an entry of the first activation map, so in the calculation of the first activation map, what things are involved? The three input image channels and the first group of three kernels. These are the two things which will be involved, the three image input channels and the first group of three kernels. So kernel 1 1 basically means this one stands for first group and this stands for the first kernel out of the three kernels which are present in this first group. So kernel 1 1 is the first of the three kernels of the first group. Similarly, kernel 1 2 is the second kernel of the first group, and kernel 1 3 is the third kernel. You can check this out as well. Like just like remember 0.1050, 0.1299, and you can see 0.1050, 0.1299. This is the first group, first kernel. That's what kernel 1 1 is. And likewise for kernel 1 2 and kernel 1 3. So yeah, the input image channels also I'm storing in image 1, image 2, and image 3. So image 1 is the first channel and image 2 and image 3 are second and third channel. This also you can verify, like I had printed the image on top as well. So after the session, you can check it out. Like the first channel of the image and this are the same thing. So yeah, now in image 1 1, you basically take that portion of the first channel of the image, which will be covered by the first kernel, kernel 1 1, to like calculate the first value of the first activation map or that first element. So this is basically in image 1 1, what I'm storing is the region covered by the first kernel of the first image channel. Similarly, image 2 1 and image 3 1 are basically the first 3 by 3 block of the second and third image channels because that's what the kernel 1 2 and kernel 1 3 will be covering for the first convolution. So here I perform convolution from scratch. Like I basically, this operation basically just like both of these are 3 by 3 tensors, right? Image 1 1 and kernel 1 1. So this operation basically just multiplies corresponding elements. So if I print it, like all these three. Each of them will be 3 by 3 kernels, of course. So yeah, this is it. And the dot product will be the summation of all the elements present in like each of the 3 by 3 matrices. So yeah, so these are the dot products. So where it like the first image channel has performed dot product with the first kernel. Second image channel has performed dot product with the second kernel, and same for the third image channel and the third kernel. So we have the dot products present, and we have the bias also stored in bias underscore one. So I had told that each entry in the first activation map will be calculated by the sum of all these quantities, the dot products and the bias. So I'm storing the first element which I have calculated from scratch as element one. So, and then I printed element one and first element. First element was what we got by passing the image directly through the convolutional layer, and element one is what we get by doing it from scratch. So you can clearly see that both of them match. So this validates our my explanation what I'd given for the calculation of values in the output activation maps. And now coming to how a max pooling layer works. So this is just the initialization. Again, it's simple. Kernel size and stride has to be mentioned. The input image size is this and output becomes this. As I mentioned before, when kernel size and stride is 2 each, what the layer does is it picks one pixel value out of every 4 pixel values of your original image channel. So that's why a 2n cross 2n image channel will become an n cross n channel when it comes out. That's what's happening here. So yeah, if you print the output will also have 3 channels, and size of each channel will be 128 cross 128. So now what I'll show you is that this is indeed the maximum of the first 4 elements of the first channel. This should be the maximum element of the second block, second 2 cross 2 block of the first channel in our image, and so on. So the first block of the first channel in our image is this. Second block of the first channel is this. See, this is the image. This is the first channel. So the first 2 by 2 grid is what this is, which I printed here. The second 2 by 2 grid, which isn't shown here, but I've shown it here. So the first entry of the first channel in our output from the max pool layer should be the max of these 4 elements, which is 197, and it is 197. The second element should be the max of these 4 elements, which is 199, and it's 199 again. So yeah, this is just this. Yeah, so we've come to an end of the code implementation. So this implementation is just to show you all what goes on behind the scenes when in channels and out channels are greater than one. And it's just to again make you all believe that how much Pytorch simplifies our work. Because just to calculate one entry of one channel of the output channels, output activation maps, we had to do so much. So imagine calculating all values. Like structuring a loop and all to do that will be pretty tedious. So Pytorch greatly simplifies our job. So yeah, that's what this was all about, the code implementation. So yeah, now I'll wait for a minute or so for any doubts, and I'll look at the chat as well.
If anyone has a doubt, I mean, from his section or from my section, you could raise your hand and we'll unmute you and you can ask your doubts.
Yeah, so someone has asked torch.manual seed 42, what does this do? So see, what this is for is, yeah. So I've done this torch.manual seed equal to 42, and I mean, I've set it to 42, and see, the next line, I'm generating a random image, right? Torch.randint. What this does is it generates a 3, 256, 256 tensor filled with entries which are integers, which are randomly chosen from the range 0 to 255. Like, see, this is the upper limit, but it's not included in the range. The lower limit is included. So I told you all earlier that each pixel value lies in the range 0 to 255 with both of them included and them being integers, right? So that's why I specified the limits in such a way. And like each pixel value will be picked at random. Now, like the reason I'm doing this at random is I don't want to put too much effort and think too much to specify each pixel with a value. But let's say that today, like yesterday, I executed this code it worked with a set of random values. And let's say today I had to present it in front of you all, right? So there's always a scope for error, right? If you again execute the code and the random values generated are something different as to what you saw yesterday. So you would like the same set of random values to be generated again, right? So that's the reason I'm setting this torch.manual seed equal to 42. So what this basically does is the values it chooses are at random, but it's for reproducibility, which means like even if I run this code again, the set of random values which like form the pixels of image, they'll be the same. Now see, for example, if I change this to let's say 20, now like just closely see this, okay? These the randomly generated image will change now. Like 102, 179, and 197. Let's say like just keep these in mind. These are the original like in the original image. Now if you change seed, it should change. Just a second, it's taking a while to execute. Yeah, so you can clearly see the values have changed. But if I again execute this, it'll remain the same because I've set the manual seed to 20. So that's the idea of manual seed. Yeah, and someone has asked why 42. It can be anything. It's just commonly taken to be 42. It's for a non-technical reason also. You can Google it. Okay, so I'll wait for maybe 30 seconds for any other doubts, or else we can back. Yeah, so I guess no other doubts. So Anshuman, we're done, right?
Yeah, I guess we can pack.
Yeah, okay, guys. So yeah, that's about intro to CNN and how Pytorch makes our life easier. So yeah, I hope you guys learned something from the session and found it useful. So yeah, we'll just end the session. Thanks for attending.
Yeah.
You guys can leave now.